This is question 10. State Lenz's law of electromagnetic induction. So Lenz's law is about the direction of the induced EMF. But the law only works if we talk about the currents in circuits. So we usually start it by saying if there is an induced EMF in a circuit, its direction will be such that a current driven around a complete circuit will produce a force which opposes the change that caused it. So it's quite a complicated law to write down because we have induced EMFs, but we need those EMFs to drive currents in order to notice this direction of force idea. So in terms of describing an experiment that demonstrates it, our usual favorite is to have a coil of wire with a north pole that can be moved both towards and away from it. And so there's two situations to describe here. So as N pole moved towards the coil, we better make sure it is a complete circuit, otherwise the law doesn't hold. So we'll do this. So as the north pole is moved towards the coil, there is an EMF induced between the coil's ends. This drives a current through the bulb. We'd see it light up. The current in the coil must produce an equivalent to a north pole at the end nearest the magnet at the right end. This will cause a force on the magnet which opposes, pen's not working, let's try another one, which opposes the original motion. So on here, if this north is moving towards, we know that the current must go around this coil in such a way that it produces a north pole at the near end. Using the right hand grip rule, I'm just quickly trying to sketch that underneath. We want the thumb to point towards the right, which means our fingers have to curl round our hand like this. So the current in this coil has to be coming down at the front, up at the back, and it produces its own magnetic field that will have a primary field line coming out here, making this end the equivalent to a north pole and this end the equivalent to a south pole. 3, discuss the consequences in the experiment which you describe if the direction of the induced EMF were other than what the law predicts. So in this experiment, we could say that in terms of energy, the important idea is to move the magnet to the left. A force must be applied to overcome the repulsion that we just described in the previous part. In other words, work is done. So this isn't answering the question yet. In the way it works normally, you do work on the magnet by moving it towards the left, and the output is that there is some electrical energy that goes to my light bulb that gets converted into light energy. If the current went the other way around this circuit, we would not need to do work to the magnet because there would be a south pole at this near end. So the magnet would get pulled in on its own and the light bulb would turn on. So effectively, we'd be getting some energy in the magnet. It would be increasing its kinetic energy and some energy in the bulb without any energy input. So to move the magnet to the left, a force must be applied to overcome this repulsion. Work is done. If this force was reversed, there would be energy created in both the magnet and bulb, which of course would break the law of conservation of energy.